Hello and welcome to today's Laser Focus World webinar, SPAD and SPAD Arrays, Theory, Practice, and Applications, sponsored by Hamamatsu. I'm Justine Murphy with Laser Focus World and Multimedia Director of Endeavor Business Media's Digital Infrastructure Group. We welcome your questions during this webinar. You can send them at any time by using the Ask a Question box. Our speakers will address them if there's time following the presentation or later offline via email. If you have any technical difficulties, just use that same Ask a Question box and our webinar team will be happy to assist you. And we recommend disabling any pop-up blocking software or extensions in your browser, as these can cause issues with the webinar player. And please be aware that today's presentation is being recorded and will be available on the Laser Focus World website within the next 24 hours. You'll be notified by email when that's ready. And before we begin, let's take a quick poll. What is the most interesting SPAD technology for your immediate or future needs? A, single channel SPADs, B, linear 1D SPAD arrays, C, small 2D SPAD arrays, or D, large 2D SPAD arrays. And now let's get started with the presentation. I'm happy to introduce our speakers, Dr. Slavomir Piatek, a senior university lecturer of physics at the New Jersey Institute of Technology and a science consultant for Hamamatsu. He's joined by Eric Mesa, a marketing engineer at Hamamatsu. Thank you both so much for being here, and let's start with you, Slavomir. The floor is yours.
So thank you for a very nice introduction. And first, I would like to thank everyone out there for joining our webinar sponsored by Hamamatsu. As we said earlier today, the topic is a single photon avalanche photodiode, or simply SPAD. We'll discuss a single element and arrays. The presentation is divided into 4 parts. The first 3 parts will be given by Slavomir, me speaking, and I'll discuss physics fundamentals of a SPAD. Then we'll talk about SPAD arrays and a very quick overview of some of the more interesting applications of SPADs. The 4th part will be given by Eric, who will discuss challenges and solutions addressed by Hamamatsu. So let's move on to technical background. So at the heart of a SPAD is a p-n junction. There are 2 important phenomena in the p-n junction making SPAD work. One is photoabsorption, where electron and Hall is produced in response to absorption of incoming photon. The second process is impact ionization. It is this process that gives SPAD a gain, which means that for a single incident photon, we can get literally millions of resulting electron-Hall pairs. For a p-n junction to operate, it needs to be biased. Here we applied a reverse bias labeled V bias. On the right-hand side, we see a plot of lack of gain, so mu is gain, as a function of bias. If the bias is sufficiently low, there is no gain. This is the regime where photodiodes operate. As I increase the reverse bias, we begin to have gain, and that is because impact ionization begins to occur. In this linear region where APDs, avalanche photodiodes, operate, the gain which results from an avalanche is self-quenching. In other words, avalanche occurs, but it quenches by itself. However, if I bias the junction beyond the so-called breakdown voltage, we enter a Geiger region where, once initiated, the avalanche will not stop unless the user stops it in some way. An important property describing devices operating in Geiger region is the difference between the bias voltage and breakdown voltage. This voltage is known as overvoltage or excess bias. Here we have a SPAD, which is biased above the breakdown voltage. On the right-hand side, we see a plot of current versus voltage. The Q point of the SPAD is a point on the V-axis. The SPAD is in this metastable state. When it absorbs a photon, the photon initiates avalanche. Current begins to flow, but because we have no quenching mechanism, the current quickly reaches saturation level and flows in perpetuity. In this combination, SPAD is simply a light switch, and it's not very useful for practical applications. However, if in the circuit, biasing circuit, I insert a quench resistor, I also inserted a load resistor from which I'm going to take the signal, I've created a mechanism where the avalanche in the SPAD is going to be quenched. It is quenched because during the avalanche, a voltage will be deposited on the RQ, which will lower the voltage on the SPAD, thus quenching the avalanche. In the middle panel, we see kind of like an engine cycle of our SPAD. We start on the V-axis, and then we move along the red line in a circle, coming back to the starting point. So the cycling engine-like performance is due to this passive quenching. From the load resistor, I have obtained the resulting pulse, voltage pulse. It is characterized by a very, very short rise time, a peak, and then slower recovery. The recovery time is controlled by the quench resistor and junction capacitance. During the recovery, the SPAD is still sensitive to light, though the sensitivity is greatly reduced. That sensitivity increases as the recovery nears the completion. So far, we've discussed passive quenching. There are two other ways to quench a SPAD. One is known as active quenching, where a sensing resistor is going to detect an avalanche, and voltage will be inputted into comparator. If the voltage exceeds the threshold voltage, we are going to pin the voltage across the SPAD, thus quenching or stopping the avalanche. The time of pinning the voltage is known as a hold-off time, which is the adjustable parameter by the user. There will be some advantages to have this hold-off time longer than perhaps just a momentary application, and we'll discuss that shortly. In the third possible quenching situation, we have a hybrid, so elements of passive quenching and active quenching. And so here, instead of having RQ, we have a MOSFET transistor whose channel resistance is being controlled by the circuitry, which is similar to what we saw in the active quenching. There are pros and cons for each type of quenching. Unfortunately, this is outside of the scope of our presentation. Let's now look at the various outputs from a SPAD. So up front, I would like to say that a SPAD can produce either no pulse or yes pulse. So it has a binary output, yes or no. If there is no light, we still are going to get pulses due to dark events. Suppose that we have very intense light. If this is the case, the output from the SPAD, idealized, I must say, will consist of a time sequence of pulses with almost no time in between those pulses. Please note that if I were to increase the intensity of light, you would not get more pulses than what is shown here. We have reached the maximum rate with which pulses are produced. Suppose I now have intense pulses with a duration greater than recovery time. In this case, I would get a burst of one burst of pulses, and these pulses would consist of one electron waveforms, plus some dark events interspersed. On the other hand, if I have intense pulses, but with a time duration shorter than recovery time, I'm just going to get a single pulse in the output of SPAD for a single light pulse on the input. So I would like to perhaps repeat important point is that if I have 2 or 3 or 5 photons simultaneously hitting SPAD, you are still going to get just one PE waveform. And finally, if I have single photons, I'm going to get single pulses with a timing corresponding to the timing of the single photons. If the photons are too close in time, I'm just going to get one pulse. Let's now discuss a dynamic range. There are two types of dynamic range one can think about SPAD. One is the maximum count rate. So suppose I illuminate the SPAD with light and I count the events at the output. Of course, as the light level is low, I'm going to get interspersed pulses in time. However, as the intensity increases, eventually I fill up all the available time on the time axis. When this happens, you have reached the maximum count rate. Here is an example of input-output characteristic for realistic SPAD by Hamamatsu. We can see a good linearity between output number of detected photons per unit time as a function of incident number of photons. And at certain rate of incoming photons, we see a deviation from the linearity and eventually flattening where we have reached saturation, you could say, in time. The other type of dynamic range corresponds to, let's say, amplitude. So again, SPAD can only produce 0 or 1, click or no click. However, suppose I now connect a counter with a number of bits n, and I'm going to count events over certain integration time. In this case, the saturation is limited not by a SPAD, but by the number of bits in the counter. And of course, how often the photons are arriving in the integration time. So the maximum count for a given SPAD is limited by the counter. A single SPAD by its nature does not have photon number resolution. Again, 1, 10, 50 simultaneous photons will simply produce one waveform. However, you can achieve photon number resolution, i.e. we want to measure how many photons we have in a photonic pulse or light pulse, having an array. So in here, in the 3x3 array, I can then determine the number, photon number in a pulse. And here is an example of the plot from the reference below that clearly shows ability of SPAD arrays to be able to distinguish the number of photons in a pulse. Let's now move on to some key characteristics of SPAD. The first one I'd like to discuss is photon detection probability, which is the product of quantum efficiency and probability of Geiger discharge. This is a useful quantity when we compare the various PN structures. And one can see a typical behavior where this photon detection probability increases with wavelength, reaches a maximum value around 400 or 500 or so nanometers, and then declines. This, of course, plot is for silicon SPAD. However, as we'll see later in the presentation, SPADs are going to be part of pixels where other components, electronics, can be placed. It's therefore a more useful quantity when comparing devices is photon detection efficiency, which takes into account a fill factor, which is simply a percentage of acreage of the pixel occupied by a SPAD to the total acreage. And therefore, here we have a plot, a realistic plot of photon detection efficiency as a function of wavelength for realistic SPAD by Hamamatsu. It should be noted that photon detection efficiency is certainly a function of wavelength, but it is also a function of overvoltage or excess bias. And so here we see a plot of, among others, photon detection efficiency as a function of overvoltage. And we see that photon detection efficiency increases with overvoltage. So before we crank up the overvoltage to a maximum, we have to realize that this may not be the optimal thing to do, since overvoltage will also control the rate of dark events. And so speaking about dark events, which is the second important characteristic, here we see a plot of a dark count rate per unit area, so dark count rate density as a function of excess bias voltage for various structures developed by various groups. And we see that in all cases, we are going to have an increase of dark count events with as a function of bias voltage. So typically in practical situations, a manufacturer is going to recommend a certain excess voltage or bias voltage or over voltage, which will optimize a performance of a SPAD. Dark count rate certainly depends on the type of material, whether it's silicon or indium gallium arsenide, which can also be used to make SPAD sensitive to infrared. However, it also depends on temperature and, as we said earlier, over voltage. So on the right-hand side, you see artist's conception of plots where we see how dark count rate increases with over voltage for a fixed temperature. And at the bottom, we see how dark count rate increases with temperature for a fixed over voltage. Unfortunately, for silicon SPADs, this knee occurs close to room temperature, which means that as temperature increases above the room, we have a rapid increase in the dark count rate. The dark count rate will also depend, when it comes to a device itself, will depend on the size of a SPAD. And so here we have a plot of dark count rate for 3 SPADs differing by the size of the active region. For a given temperature, we see that the rate increases with increasing size. Another crucial characteristic is time resolution, or also known as jitter. So jitter represents a variation in the transit time or response time. I'm going to illuminate my SPAD with single photons, and for each event, I'm going to carefully measure the response time. In practice, this is not an easy thing to do, but it's possible. And we are going to plot the histogram of these transit times, and the width of the distribution, the full width half max, represents the jitter. When we compare jitters among detectors, the comparison should be done for a single photon. It turns out that the jitter is a function of over voltage, and for some devices, it will be also a function of number of incident photons. In case of SPAD, it doesn't matter, single photon generates the response. Okay, so here are some realistic plots. On the left-hand side, you see example of such histogram with a full half max of about 36 picoseconds. But please do note the long tail with rather long time constant. Jitter also seems to depend on temperature, as we can see on the right-hand side. For a certain bias voltage, we see that for higher, the jitter will increase with increasing temperature, or it's lower, which is good for a lower temperature. Let us now discuss some characteristics that are not so desirable in operation of a SPAD. And one of them is phenomenon of afterpulsing. So in ideal case, I have a SPAD, a photon initiates the avalanche, I have a pulse coming out of the SPAD, and after a full recovery, I'm back to a light-sensitive state of the SPAD. However, in realistic SPAD, what can happen is that during the recovery, shown at the bottom panel, I can have additional pulse produced. So this is known as afterpulsing, and this pulse is going to have lower amplitude than the primary, and it's due to a charge being released in the SPAD's crystal structure producing the secondary avalanche. So again, after pulsing, this is also a reminder to us that during recovery, the sensitivity of a SPAD is not a zero. If it were, you would not have after pulsing. So after pulsing can be controlled with a hold of time in active quenching. And so in the top panel, I have a shorter hold of time than in the bottom panel. And so if the hold of time is long enough, then I can suppress the after pulsing, because the charge is going to get released, but it's not going to produce an avalanche. After pulsing is a function of temperature. And as we see from this plot showing after pulsing probability density, when the temperature is low, so green, the probability is higher compared to higher temperatures. And so here you see kind of a compromise, a trade-off between after pulsing and dark counts. So dark counts will decrease with decreasing temperature, but we are going to increase the probability of after pulsing. So now when we have a SPAD array, so more than one SPAD, then we have to do with yet another undesirable phenomenon, which is a crosstalk. So suppose I have a primary discharge as shown by the yellow cloud on the left-hand side. This discharge is going to produce photons capable of triggering avalanches in nearby SPADs. And so those are shown in blue. We have two of them. And so since the transit time of photons is very short, instead of getting one pulse, I get 3 pulses from this SPAD array, 2 of which are artifacts of a crosstalk. Before we move on to SPAD arrays, I would like to point out that the actual structures of SPADs are certainly much more complex than the simple PN structure I showed in the first slide. There are multiple layers of PNN materials which are needed to shape the electric field in the structure for the SPAD to operate optimally. So SPAD is not the photodiode biased into a Geiger region. That would not work. There are generally two types of structures, thick junction, shallow junction. The shallow junctions are typically used in arrays. And on the right-hand side, you see a structure made of indium gallium arsenide, indium phosphate, and this structure is sensitive to infrared radiation, a highly desirable part of electromagnetic spectrum for numerous applications. This table, which is best viewed in one's privacy, gives some basic characteristics and range of characteristics of silicon SPADs. And this table compares some aspects of silicon and infrared SPADs. There's one thing I would like to point out, however, in this table is the sensitivity wavelength of the infrared SPADs. So they are going to be sensitive somewhere between 1,300 and 1,600 nanometers. So with this, let's now move on and discuss SPAD arrays. Let me begin with the most familiar to all of us, which is a silicon photomultiplier. Yes, SIPM or MPPC, as it's called in Hamamatsu, is a SPAD array. A single element here, a microcell or pixel, is a series combination of a SPAD and the quench resistor. In this array, however, all the microcells or all the pixels are connected in parallel, and therefore we just have 2 prongs, anode and cathode. This structure is a chronological summer of pulses. So if I have 2 events in 2 microcells simultaneously, I'm going to get a 2PE waveform as indicated in this slide. So again, SPAD will always give you individual waveforms, whereas in silicon photomultiplier, a SPAD array, you can get pulses with amplitude proportional to the number of incident photons at a given moment. So let us now compare SPAD pixel to other familiar pixels like CCD and CMOS. So first, in case of a SPAD pixel, I can have the SPAD structure, and I can also have electronics built into the pixel. In case of a CCD, charge-coupled device, no electronics integration is possible in the pixel. The pixel can only operate in the integration mode, and for a standard CCD, charge readout is done by clocking charge or moving charge from pixels to pixel. But now let's move on to CMOS. So in case of CMOS, yes, you can have electronics also put into the pixel. So what is the main difference between SPAD and CMOS pixels? The most important difference is that SPAD has a gain. One photon can produce 1 million electrons, whereas in CMOS, one photon can at most produce 1 electron. So therefore, in CMOS, the readout noise is very important, and it's going to limit our ability to detect, for example, individual photons. It became possible recently to do that for certain types of readouts because the read noise has been reduced to a small value. However, in SPAD, again, we have gain, and so the read noise is not an issue. And therefore, in SPAD, we can put types of electronics, like, for example, timing electronics, which might not be optimal for a CMOS. Let's have a quick comparison between SPAD array, CCD, EMCCD, and CMOS. There are various entries. All of them can do imaging, but please note that for CCD, EMCCD, and CMOS, the imaging or the dynamic range is limited by the capacity, full well capacity, whereas for SPAD, we are limited by the counter. And so if we have enough bits in the counter, there is effectively no limit in that amplitude dynamic range. Another important point is that we can have single photon detection in the SPAD array due to gain. We can have photon resolution, and very importantly, we can timestamp events in SPAD array, something which is not possible for CCD, EMCCD, and CMOS. There, you can only tell arrival time of a photon to within the integration time, whereas in the SPAD, you can timestamp individual events. Again, you can have pixel electronics in a SPAD and CMOS. No pixel electronics is possible in a CCD or EMCCD. And pixels in a SPAD array are addressable. So are they in a CMOS, but not in a CCD and EMCCD. So speaking about the circuits that you could implement in a SPAD array, so apart from transimpedance amplifier, not shown here, which converts current to voltage, I can have analog to digital converter. I can have time to digital converter. This is the one that can perform time stamping of events. We can have gating circuits, so we can control when the SPAD is sensitive to light and when it's not. We can implement histogramming electronics within a single pixel. We can also implement coincidence detection and very importantly, quenching circuit, again, ranging from a single resistor to a more complex active quenching. So in this slide, we see a progression of a pixel. So on the left-hand side, we have the simplest possible pixel, which has a quenching circuitry and the transimpedance amplifier. In the middle pixel, we've added n-bit counter. So in this case, the output from this pixel would be the number of counts, not pulses, but number of counts within certain integration time. And in the third pixel on the right-hand side, we've added also a time stamping circuitry, which means that the output will be not only the number of events, but also their occurrences, their times. Electronics integration in a SPAD array can be performed horizontally, which means the pink here represents the electronics. So you can have electronics in the pixel. You can have electronics outside of the pixels. So this is known as horizontal integration. Another approach is to have a vertical integration, where we have two layers. The top layer is the one that is sensitive to light, and that top layer is then connected via bonds to a bottom layer, which contains the appropriate electronics, driving individual pixels and the whole array. Here we say micrograph of a vertical integration. So I know you cannot see the mouse, but there's a SPAD here. There's a copper bond, ASIC, and this particular structure also has microlens, which is increasing the photon detection efficiency. So here you see an example of a SPAD, a linear SPAD array. So where we have light-sensitive SPADs, and nearby in the horizontal configuration, we have electronics that drives these SPADs. And here is a micrograph of a realistic structure. So on the right-hand side, you see the two SPAD pixels in orange, and to the side in blue, you see the electronics associated with these pixels. And this particular pixel has a pitch of 24 micrometers. Then we can have a 2D arrangement. So here is the artist's conception of such a 2D arrangement. Again, pink represents the electronics, and there are numerous bus lines that are going to address and control the pixels. And please note this micrograph that shows a pixel from a 2D array. Incredibly, the SPAD itself occupies a rather small fraction of the entire pixel, where numerous circuits are realized. So with this, I would like to now quickly go over some applications of SPAD, single elements, and SPAD arrays. Most of these applications will have one theme in common, which is ability of a SPAD to timestamp events, something that other detectors cannot easily do. Remember, for imaging devices like CCD and CMOS, you can only tell arrival of photon to within the integration time. So I would like to begin this quick overview with fluorescence lifetime imaging. So if I excite a fluorophore, a molecule that will emit subsequently light, the emission of the light from the fluorophore is probabilistic, and therefore there is certain characteristic time of the decay. So if I were to repeat this experiment many times, I could have a plot as shown at the bottom of the slide showing the log of intensity as a function of time. So this line represents kind of like a characteristic decay. However, we know that this characteristic decay is a function of fluorophore's environment. For example, the temperature, pH level, presence of oxygen, or the presence of nearby fluorophores. And in certain situations, we are interested in that environment of the molecule. And if that is the case, we would like to perform fluorescence lifetime imaging. So what we want to do is to determine that decay plot shown here in the lower left corner. I have a red line, which represents a molecule in, say, vacuum, right? And then perhaps a blue line represents the same molecule, fluorescent molecule, but in some environment. And we can see that the time characteristic has changed. In this case, we are going to use a pulsed femtosecond laser to initiate the fluorescence, and one determines histograms of the resulting fluorescence, from which then we can determine the the decay the decay characteristic. And so here we see an example from the reference below showing that with a SPAD array, you can certainly not only get intensity, that's kind of like a bonus, you get intensity image, but also the image of the lifetimes, which using color coding, we see that it changes in the image field. So there are some advantages for using SPAD. It's a higher count rate due to pixel polarization, on-chip processing. Again, we already said about time stamping, but also you can do a triggered operation, right? So you can only observe fluorescence in certain time windows, and that will affect efficiency with which we can construct those decay plots or histograms. Let's now go to fluorescence correlation spectroscopy. So this is a technique that can be used to study, for example, molecular diffusion, concentration fluctuations, and others. The basic idea is that I'm going to focus light on a small volume in my sample and simply measure intensity variations of light, detected light, from that volume. Once we obtain this time-dependent intensity, we perform autocorrelation and compare the autocorrelation function to the models depicting the physical phenomenon. These measurements can be done using the famous Hanbury, Brown, and Twist configuration, which will use single-element SPADs, or one could use a SPAD camera, where in this case, you can get information from multiple points in the sample, which will be illuminated now with a light sheet. There's a very interesting reference, Synth and al., which used various techniques, SPAD array, CMOS, scientific CMOS, EMCD, etc., to measure a diffusion coefficient of some sample beads. And the bottom line shows the diffusion coefficient, and please note the errors, measurement errors. So the two approaches using SPADs have the smallest errors compared to other techniques. Another interesting example is super resolution microscopy. By super resolution, we mean imaging where you can beat the diffraction limit in classical imaging. Here, a structure under investigation will have attached fluorophores, which then will be excited in such a way that only some of them are emitting light for a given excitation cycle. You perform these excitation cycles many times and construct the final image. So what happens is that in the object plane, our source fluorophore is effectively a point source. But because of diffraction in the image plane, what we get is the light distributed. That distribution is known as point spread function. So using SPAD, I can sample this point spread function. And again, SPADs are sensitive to individual photons. They have very high sensitivity. And therefore, if I then know the PSF, if I've sampled the PSF, then I can accurately determine the centroid, i.e. tell where the image center is in the image plane. And so here we see an image or three images of the same field using SPAD array, EMCCD, and a conventional wide field imaging. And you can see visually that the SPAD array here performs comparably to EMCCD. Another interesting application is remote gas sensing. I'm just going to concentrate on methane. In this case, our SPAD is going to be part of a system known as LIDAR, gas LIDAR. And the basic idea of gas sensing is shown on this slide. I should point out that there are other approaches. This is the one where a SPAD array could be used. So we have a laser that produces a short pulse of light with wavelength that is going to be straddling the absorption feature of methane. So the light goes to the right, and due to backscattering, some photons are going to come back. What a SPAD array will do is going to measure time of flight from which you could determine the distance to the scattering centers. And you would obtain some plot signal as a function of a distance or delay. However, if I now introduce methane, then that plot is going to be altered by the presence of methane, because the methane is going to absorb the photons, and so the return signal is going to change its characteristic. Here on this slide, we have an example of actual realization of this idea using SPAD array, and on this slide we see visual results of that methane LiDAR. So we have the famous point plot. However, in the panel D, removing background and other contributors, the bright feature here represents the distribution of methane in the field of view. I would like to discuss now quickly another interesting application, which is a quantum key distribution in quantum communications. So first, I would like to say that there is no way that a classical distribution, channel is immune from eavesdropping. Every classical way of communication can be eavesdropped without detection. What we currently do in communicating is that the sender and recipient are going to share what's known as the private encryption and decryption key. But please note that this key has to be somehow distributed between the parties. So as we stated earlier, there is no way to perform such a distribution in such a way that we are 100% immune from undetectable eavesdropping if the exchange is classical. Incredibly, in 1984, there was an important paper referred to as BB84, which showed that using quantum states of photon in polarization, one can transmit information in such a way that any attempt of eavesdropping will be detected. So this offers a way of transmitting information in such a way that we can have a complete privacy. In other words, if you detect that there was eavesdropping, you simply scrap the transmission and try over again. To perform this quantum key distribution using BB84 protocol, what you need is a single photon source and a single photon detector with properties such as negligible dark current and nearly perfect sensitivity. Such detectors almost exist, like nanowires and edge sensors. However, for example, this recent article showed that you can perform BB84 protocol using a single SPAD, and the efficacy of this approach is shown by the qubit bit error rate, shown in red dots, which is slightly higher than the theoretical error rate. Another interesting application is a 3D radiation detection. So here I have a scintillator where scintillation occurs using a SPAD array, which again can timestamp events. It is now possible to not only detect these scintillation events, but also we can tell where those events occurred within the scintillator or the sample. So this opens up many possibilities in, for example, medical imaging or security imaging. So one obtains multiple images and measures times, and then algorithms are going to calculate the origin points of those events. And here, this slide shows a practical realization of a system which is capable of this 3D radiation detection. Time is short, so this is my final application, which is time domain functional near-infrared spectroscopy. So the basic idea of this approach is to study properties of media, such as, for example, human brain. In certain wavelength, a human brain will be characterized by certain absorption coefficient and scattering coefficient. These coefficients will change with time and also with mental activity. This is of great interest to those that study the human brain. The approach is basically like LiDAR. You inject light, and then you measure arrival time of emerging photons. What one constructs are histograms. These histograms will depend on the separation of the probes, and will also depend, they also have to be deconvoluted from the instrument response function. But the bottom line is that a histogram like this can yield information, unambiguous information about mu A and mu S, whereas other techniques like continuous wave approach do not provide that information. So SPAD and SPAD arrays made, I don't want to say revolutionized, but certainly made this approach, histogram approach, now viable compared to the past where PMTs were used, which offered a number of features that were not desirable for practical realizations of such systems. And so with this, I would like to end my part. And now Eric is going to discuss how Hamamatsu is addressing the various issues we discussed in my part of the presentation. So thank you very much for listening.
Great. Thank you so much. And before we get to Eric, right now we're going to do another poll question. What manufacturer of SPADs are you currently using or buying? A, Hamamatsu, B, other suppliers, or C, not yet using a SPAD solution? And so let's now turn things over to Eric. Take it away.
Okay, thanks, Justine, and thank you, Slavomir, for that really informative foundation on the physics of SPAD technology and also covering some of those key applications. Now I'd like to delve into, as Slavomir mentioned, some of the challenges currently limiting SPAD performance and how we're approaching to address these challenges, and the innovations and manufacturing capabilities that Hamamatsu has that are aligned to meet those industry demands. So let me move on to the next slide here. These are some of the main SPAD characteristics that we're focusing on in terms of resources and expertise on what we need to improve, again, based on what the needs are of the industry. We also do want to remain flexible, of course, when looking to improve these hypotheses in terms of what's important for particular applications and the direction of SPAD technology. So how are our manufacturing capabilities aligned? I mentioned, and Hamamatsu is vertically integrated, from end to end with semiconductor manufacturing capabilities, from advanced wafer fabrication, which we may refer to as the back end, all the way through to precise, assembly processes as well associated with semiconductor manufacturing on the front end. So this manufacturing know-how is really what enables Hamamatsu to tailor these custom solutions with very high quality at a large scale. So moving on to talk about these, challenges and improvements. So PDE extremely important for enhancing signal to noise ratio, which provides accurate measurements or helps provide accurate measurements in time-sensitive applications or light-starved applications, I should say, like LiDAR or fluorescence, microscopy. PDE, there's a distinction to be made also between PDE and PDP, which is PDP refers to the probability of detecting a photon just based on the structure of the detector, where PDE is really the true sensitivity of which incorporates all of the other factors such as geometrical efficiency, the optical losses, and various other efficiencies that contribute ultimately to your true sensitivity of the SPAD. So how we're working on improving these things, micro lenses, for example, can help improve the light collection efficiency and the overall PDE of the SPAD. As I mentioned, that's sort of related to the geometrical and optical losses portion. These micro lenses are deposited on top of the SPAD, but of course they do have some scalability challenges in terms of precisely aligning these micro lenses to each individual pixel, especially as pixels become much smaller and smaller and more challenging to do. So to combat that, we're also working on next generation lens technologies that use advanced lithography techniques in order to deposit, this next generation lens technology on top of the SPAD, which is much better suited for scaling up for, high density arrays and very precisely, as well as increases in efficiency in terms of light collection. And then additionally is optimizing the internal structure of the SPAD. So on the sensor side, in terms of the structure, we have both front illuminated and back illuminated technologies. And specifically for NIR light, we can use this back illuminated SPAD structure, which has a thicker, essentially epitaxial layer, which allows one, in terms of back illuminated design, it moves the avalanche region further down into the detector. And it's a thicker structure, which allows you to capture those deeper penetrating NIR photons. And then, but front illuminated is still very useful for maybe 1D or single channel SPAD sensors because of the location of the interconnects on the front illuminated side makes it more better suited for those single channel or 1D array type of applications. So moving on now to discuss dark noise. So we have a lot of experience with integrating thermoelectric cooling into our detectors to effectively suppress, dark noise and dark counts in SPADs. And this is really critical for applications that require really ultra low dark counts, like quantum sensing or biomedical imaging. However, each cooling stage does increase the cost of production and system power consumption as well. So it's a trade-off that does need to be balanced based on the needs of the application. To look at our short-term development timeline as it relates to dark noise suppression and PDE improvements by way of, I mentioned, the internal structure optimizations to improve PDE, as well as the micro lens technology that we're looking at to help improve the light collection efficiency and reduce the dark counts. Now moving on to the sort of next major challenge that we see is increasing the maximum count rates. And the most immediate way that we're looking at improving the maximum count rates is by upgrading the quenching mechanism or the reset mechanism of the SPAD 2 versus passive quenching. So the maximum count rate, which is limited by the dead time or the reset time of the SPAD, is an active quenching circuitry. So this reduces the dead time essentially and increases the maximum count rate dynamic range for applications needing that higher dynamic range, like correlation spectroscopy measurements or particle counting or particle analysis. And then moving on to other sources of noise that we're looking to improve or suppress. such as Afterpulsing and Crosstalk. Crosstalk is specific for 2D arrays, but an approach to reduce afterpulsing is also by use of active quenching circuitry, which it can be designed in a way to have some control on the hold-off time, which essentially turns off the avalanche like a switch, as Slavomir kind of mentioned it earlier in the SPAD. So you can kind of increase the hold-off period of the SPAD where an avalanche cannot be triggered, which ultimately reduces your probability of afterpulsing. But of course, it's an important trade-off as well to think about that increasing your hold-off time will essentially is increasing your dead time, which will lower your maximum count rate. So again, there's always trade-offs with improving certain features in terms of how it affects some other potentially characteristics. And Crosstalk, as I mentioned, which is a that is specific to 2D array designs, essentially the triggering of a neighboring pixel during one pixel's detection event. And these crosstalk phenomena can be addressed by depositing deeper trenches that fully isolate one SPAD pixel from a neighboring SPAD pixel. And on the right side of the screen here, you'll see data showing the differences between, with deep trenching and without deep trenching, and how the crosstalk can be significantly improved by addition of this deep trenching technology. So just to kind of quickly, Slavomir talked in great detail about horizontal integration or vertical integration, digital SPADs versus ASIC integrated SPADs. But Hamamatsu has essentially chosen to really focus on the vertical because we believe this allows the best benefits for SPAD array designs in terms of high fill factor, which leads to better sensitivity for the SPAD, as well as better in terms of scalability, right? When you design, you're able to design your electronics with more flexibility in terms of the readout. It makes it a better scaling in terms of the semiconductor manufacturing process. And but of course, again, thinking about the drawbacks in terms of the vertical integration, there is some increased design complexity and therefore cost as well. So how are we approaching array and electronics design? So we understand that sensor technology is really important, as well as the electronics design as well. So I mentioned the vertical stacking and direct bonding types, but also customization of those sensor structures and the functions that you're building into the ASICs. And I mentioned crosstalk as well, but it does relate to the design of the arrays as well. So benefits of the direct bonding I mentioned, other benefits include besides fill factor, reliability is also a benefit in terms of the bond between the ASIC and the sensor being much more robust when you do this direct bonding or the stack technology, which makes it more robust for high humidity or high temperature type environments. This is another big benefit as well. And so it's important, again, to be flexible and be able to customize. And this is an approach that we're looking to take with our 2D SPAD array development is, this is a basic configuration example of a SPAD plus ASIC, but there's various different customizations that can be added in terms of the functions that are built into the ASIC or the FPGA or the sensor itself in terms of the channel number, pixel number, or the pixel size and pixel pitch. This is an example of a TDC function, a time to digital converter, which essentially is a time tagging function, which gives you time information. So this is just kind of the basic block diagram of how we're looking at the sensor and the ASIC and FPGA. And so we focused on providing these integrated full sensor and module solutions. But of course, how we get there depends on the user case and the application. The important part is for us to really remain agile and flexible to tailor our solutions to the needs of the industry, as I mentioned. This is a quick look at some of the newer generation single element SPAD modules that we have releasing this year. We have feature updates on the silicon versions, as well as new in-gas SPAD-based modules for NIR photon counting applications. So feel free to reach out to us for more information on any of those offerings. And lastly, just want to mention an upcoming event that we have. We'll be at Photonics West and BIOS starting this weekend going into next. So do feel free to visit us if you're attending Photonics West. I'll be at the booth for both BIOS and Photonics West. Would be happy to see you and talk to you there. We have some talks going on. For more talks or information specifically on SPADs, Slavomir will be giving a course on the 26th about various different photodetector technologies, including SPADs. And then we'll have a roadmap and strategy update from our CTO of the solid state division, which covers SPADs at the booth on the 28th as well, along with many other talks going on. So yeah, thank you.
Fantastic. Thank you so much. And we do have one final poll question for you. What potential SPAD applications are you interested in? A, fluorescence lifetime imaging, B, fluorescence correlation spectroscopy, C, particle analysis and counting, D, quantum, E, LIDAR, F, Raman spectroscopy, or G, something else. And we are now out of time. So on behalf of Laser Focus World and Endeavor Business Media, I'd like to again thank Dr. Slavomir Piatek and Eric Mesa for a great presentation, Hamamatsu for sponsoring today's webinar, and of course, all of you too for joining us. Enjoy the rest of your day.